Welcome back, everyone. This is another edition of the Qdrant 1.7 update. I managed to get the CTO of Qdrant itself on here to talk to me about the 3 cool things that they have done to Qdrant since this gigantic update. It's been a monumentous effort on your team's side of things, I would say, and you have done first. This fucking thumbs up. I don't know why. You have done first the sparse vectors. You also have done custom sharding, and we have made videos about each of those if you are interested in either of those and what they do and why they are useful. In this video, we're going to talk about the discovery API and what that means and what some use cases are. So break it down for us, Andre. What exactly is this discovery API?
Sure. Hello, everyone. And Discovery API is particularly a pickle because it is something which doesn't exist in any other databases. There is no research, at least known to our team, and it's something we implemented internally from the very, very scratch. We basically invented this approach from ground up.
One of a kind, basically.
Exactly. That's why it might be particularly hard to explain, because it's something, if you need to fit in a few minutes talk, and at the same time, there are a lot of fundamental stuff going on there. So I will try to do my best anyway, and if you would have any comments, please join our Discord and ask me or somebody from our team about it, because it's really something we are very excited about. We see that there's going to be a future of vector similarity at some point, but it needs a lot of education to reach this point first. So here on my slide, it's a typical example, a simplest discovery query. And as you can see, it's pretty, from some point of view, it's similar to search because it has this target vector, but it also has the second part, which doesn't exist in regular search, which is a context. And context consists of an object which have a positive and negative part. And those numbers, those are just a reference to some existing record in a database. It can as well be separate vectors, but just for example purpose, I put IDs there. So you can consider the positive example as another vector from database or from your input. And as a result, to do a discovery search, we need 3 vectors minimum. It can be more, but let's consider for now that it's 3 vectors. But before we go into discussion of how exactly discovery search works, first let's talk about motivation, why we need it. The first motivation is ability to provide a real-time context for the search query. And just to give you some intuition about it, I want to do this anecdotal example of what I had to do for the preparation of this.
I think I know what's coming. Is it a photo?
Yeah, it is a photo. It's my favorite slide, by the way. So just imagine you want to find the thing on the internet.
And for those that are only listening, this is a photo of, let me try and explain it for you, and so that you know how crazy this photo is. It's like a mix between a dragon with a wizard's face, and it has 3 different tentacles coming off of it and a long tail that's tied in knots around the tentacles. And then it has human legs with cowboy boots on, or elf boots. I don't know what they are. I'm not so versed in the lore. And on top of these 3 tentacles at the top, there's 2 sun heads, faces type thing, and 1 like reptilian face. So that's like my very, very basic understanding and description of it for anyone that is only listening. And the last thing that I will say is one of the sun faces has scissors that's coming off of it, about to cut off its own tail. So you can imagine how confusing this is to try and search for. What description do you give Google to make that pop up?
Exactly. And imagine you just saw it somewhere, so you cannot use reverse image search, and you do not know the exact name of the thing. And by the way, this name exists, so if you know the name, it's pretty easy to find. But unless you know how it's called, you will never find it. Trust me, I spent several hours trying to do so, and I was not successful. So let's see how you would try to approach the problem, right? So first of all, as you mentioned, Demetrius, you can try to just describe the thing, and you can try to put this description into Google or into the model which will convert text into vector and compare this vector with images, something like clip. But at the end, I assure you, you will not get the right results from the first try. It will find a lot of things, but none of them will be exactly what you were looking for. So you can try to adjust your query. You can try extend the description or try different words. But at the end, you do not know in advance if your next attempt will be closer or further away from what you are actually looking for. So this process is very random, and it doesn't guarantee you the improvement, any improvement of the results. So more you try, you can stay in the same very distant area and even do not go any closer to your goal. What you can try next, after you already exhaust all attempts, you can try to do similarity image search. So you find some first results, and you see that some of them are closer than others. So you can try to click on those which you think is closer, but after you do it several times, you will quickly find out that you are stuck in this bubble of similarity. Whenever you click the next page, it will show you the same results, but maybe mixed a bit. And that's because Google does not have any context of your search longer than a single query. Whenever you click on the similar image, it will just search for those images which are similar to the last one you click, and it will completely ignore the whole previous history of your interaction with the search system. And you will find yourself in this sort of bubble. You will not be able to escape, and you will just see all the same images all over again. And again, it will not help you to find the picture you were looking for.
Situation is bleak right now.
Yeah, the only possible way to find it is just scroll to page number 125 or something like this to just brute force your search through Google. Otherwise, I don't know how else you could find it. Yeah, that was the first reason for first motivation for discovery search. And the second motivation is actually a combination of multimodal vectors in a single request. If you try to do it with some existing API of Qdrant or other search engines, you will find out that whenever you try to combine text vector and image vector in one request, one of them will always dominate the other 100%. If you are searching through other images, vector image will always dominate text search. And if you are searching through text, the text will always dominate the image vector. And that's because the structure of the vector space is a bit more complicated than we might naively consider it. So that's an example.
Wait, one second, because I'm trying to see if I'm following you on this.
Sure.
Basically, the first key reason for creating this discovery API is that sometimes there are images or maybe words that we know but we don't know. It's like, what was that thing? Or we have one reference, but we can't quite name it. And so this helps with that. Second reason is because depending on what you are doing, if you are doing image search, you're going to get a lot more images that are coming up. It's more heavily weighted towards images. Or if you're doing text search, you're going to get related text. And so what you want is something that is the correct one, be it text or image. And you don't want to weight too heavily for either one of those. You just want the right answer.
Yeah, so we want to combine both text and image in single request and make it actually work efficiently. So for example, if you want to search for a chair, but you want this chair to be red, so you can combine text like red chair plus a picture of specific design which you want to be in red. And in this case, if you do it with just recommendation search or just combine the vectors, it won't work. And that's because the structure of this multi-modal or cross-modal embeddings is a bit different. It's not as plain, as flat as just regular embeddings. And the reason for this is, of course, the training process. When you do training for those cross-modal embeddings, you basically have two types of, they call it towers, two types of encoders, one for image, one for text, and then after you have those, you align them between each other. But this alignment, it doesn't guarantee that vectors will be fused together. They will still be in two separate planes, but those planes will be arranged so text of the chair is closer to picture of the chair if you don't have any other texts. Let's call it like this. So it's relative distance, it's not absolute distance. And internal structure just don't allow us to directly manipulate this vector, and it forces us to consider more elaborate ways of how to introduce this context or additional information from text into image search.
So basically what you're showing right now is how in vector space, images congregate with other images, text congregates with other text, and you may or may not get lucky that the text and the image, the corresponding image, are together or they are related in this vector space.
They most likely related only relative to other images, but in absolute sense, they are not. But pretty much guaranteed they're not. That's why we need different strategy. We cannot naively combine vectors. And how to do this is a bit, again, it might look complicated, but at the end it's quite simple if you imagine how it works internally. So, but no worries, we have pictures, so we will try to explain it in the simple terms. But for those who is proficient with machine learning, who try to train their own embedding models, that might be interesting for them. So what we did, we actually took inspiration from the loss which is used to train metric learning models and adapted it to the case where we already have a trained encoder, but we do not have all the components of this. It's called triplet loss. So what you see in the picture is a typical example of how we want to convert our vector space to put a positive example closer to anchor and negative example further away. But when we do search, we already have vector space. And what we need is to find the anchor, given the positive and negative example. It's exactly what I showed in the first slide, where we have a target vector and the context. And the context consists of positive and negative example, and anchor is our search result, what we are trying to find. On the storage, or on the collection level, it looks like this. We we have our list of vectors, and each pair of context split this storage into two parts. The one vectors which are closer to negative and other vectors which are closer to positive. And we want to search only among those vectors which stays closer to positive, but at the same time, we do not create this bubble of similarity around the positive context example. So we just split the vector space into halves. And this can be done for multiple pairs, so we can split vector space multiple times and create multiple regions like this. On this picture, we have two pairs. Each pair splits the vector space one time, and as you can see, there are four regions. One of them is heavily negative, two others are neutral, and one is strongly positive, the one here. And what we want in the discovery search, we want to search only within the strictly positive region, or in the region which have the biggest positive score. And once we have this, we use our target to search through those vectors which stay in positive region and ignore all the vectors which are in the negative one. In this case, as you can see, the separation of our collection allows us to ignore this pair of vectors and only search and only give the result those yellow ones.
And now the target is another way of saying the anchor?
No, anchors are all the points here. So we test each point to be like how good it fits the definition of anchor, and we see that those on the negative side, they do not fit. Those on the positive, they do fit. And the target is the second step, actually, after we find the appropriate region. We find the points which are closer to the target within this region. And again, to give some practical examples, what you can do with this is what we have here. So in Qdrant with discovery search, you can do a following thing. You can search for a pizza, but instead of just searching for the pizza, you provide additional context to your search query. You say you want to consider meat as negative and fish as positive context. And what you get as a result is those pizzas which are closer to fish than it is to meat. As a result, you will get salmon pizza. This trick you can do not only with ingredients, you can also do it with overall appearance of your pizza, something you cannot describe with just words. So you can give example of McDonald's dish in the negative part of the context, and you can give a fancy restaurant in the positive side of the context. As a result, you will get fancy pizza.
Then you have gourmet pizza. Yeah, I see.
Exactly.
And it can be done with both text and photos. So
yeah, exactly.
Theoretically, we could say in the negative, like the text, like steak, and then in the positive, fish. But it feels like that isn't as special because it's not multimodal.
But still, it's something which gives you precise control. So imagine you're searching for pizza, and the first result on your page you do not like. It's not enough. You want to go deeper. So instead of describing your dream pizza, what you can do is you can click that you like something and you don't like something else in your result. And the second iteration of the search will be much more precise, will be much closer to what you're actually looking for.
So going back to that idea of the search that you are doing for, I think it was vitamins that you had a few slides back. How
It's
would
actually
this...
example of bad request, right? So
yeah.
The example here is where we want to find the burger, but the first search result showed me that it found not the burger itself, but the plate with a picture of burger on it. And I consider it as a negative example. So what I wanted originally to have in this request is pictures of burgers, but not the plate, the actual dish. And in this case, this image completely dominated the search. So instead of having burgers, I have just a random sampling from the vector from image catalog.
It's some, I'm presuming it is some vitamins that you should take if you eat too many burgers.
Right. Right. So they have nothing to do with burgers because we consider this example as negative and it's dominated. So we got the result which is as far from burger as it possibly can. That's not what we meant by using burger text as a positive.
Okay, I see. Now, how do we use it in Qdrant itself? If we want to get started with this, what do we do?
In Qdrant itself, it's very simple. So the target is your text query. The positive is a vector of the fish. A negative is a vector of the steak. And you will see salmon pizza as a result.
And the limit there is just the search result limits?
This is how many results, yeah.
Yep. Okay, that makes sense, and that seems easy enough. I want to see what people end up doing with this. What kind of use cases are people coming up with once this is out in the wild? So if you are building with this and you have a use case, we would love to hear about it because this feels like something, as Andre said, is very novel and it could be a game changer for a lot of different use cases. So if you are putting this into your product, let us know. We'll ship you over a shirt.
Cool. Thank you.
Awesome. And that is all for today. Check out number 1.7, the newest update with the Qdrant product release. And that is what we've got, folks. See you later.